Good evening, students. Today we are going to discuss the topic on Cauchy's theorem, a partition of permutation and related theorems. First statement of the Cauchy's theorem: if P is a prime number and P divides order of G, here order of G represents the number of elements of the group G, then G has an element of order P. So now we explain this statement by giving a simple example. Suppose P is a prime number, 3 is a prime number, a number of elements in the group G equal to 21. Then we see that 3 divides 21. So then we have to identify one element whose order is 3 such that a power 3 equal to E in the group G. So this is our theorem. We are going to prove it now. So now, given that P is a prime number and P divides the number of elements of the group G. Now we have to prove that there exists an element of order P such that a power P equal to E, where A is an element of group G. This is the result that we are going to prove it now. Now using this induction method, we can prove this theorem. Now assume that the number of elements of the group G equal to 1. So therefore automatically we know that the identity element E is the only element in group G. Then whose order can be written as E power 1 equal to E. So therefore the order of the element is E is 1. Now there is nothing to prove. Now let us assume that the result is true for all the groups T such that whose order is less than the order of the group G. That is, number of elements of group T less than the number of elements of G. Now since P divides, the result is true for all the groups. So therefore the prime number P divides the order of T. Now by result, by the statement, there exists an element A belong to T such that a power P equal to E. Now we take a subgroup H of G and P divides the number of elements of the group G, number of elements of the group H. Then there exists an element A belongs to H such that a power P equal to E. Again we are applying the results. Now we know that H is a subgroup of G. So therefore every element of A belongs to H will be automatically in the group G. So therefore an element A belong to H can be considered as an element of A belong to G. So therefore a power P equal to E. Now next we assume that the prime number P does not divide the order of the any proper subgroup of G. Now let us assume that the prime number P does not divide the any order of the any proper subgroup of G. We have to identify one proper subgroup. Now take the class equation. The number of elements of the group G, order of G equal to order of Z of G plus summation order of G divided by order of N of A, where A element does not belong to the center of group G. Now N of A represents the normalizer of the group, normalizer of an element A. Now we are going to show that we know that already we have seen that suppose an element A does not belong to the center of the group G, then automatically the normalizer of A will not be equivalent to G. Now we have identified one proper subgroup normally N of A, and which is not equal to G, and also this proper subgroup is not divided by the element prime number P. So from this we conclude that N of A is a proper subgroup of G. Now the number of elements of the group G can be written as order of a number of elements of N of A into order of G divided by order of N of A. Now P divides order of G imply P divides the order of G, we can the previous we substitute here order of N of A into order of G divided by order of N of A. P divides the A into order of G divided by order of N of A, which implies P divides order of G divided by order of N of A. So now we have proved that for any element A does not belong to Z of G, the prime number P divides the order of G divided by order of N of A. So this is true for all the elements which are not in Z of G. So therefore P divides the sum of order of G divided by order of n of A, where A does not belong to Z of G. Now we know that P divides the number of elements of the group G. So let us go to the previous slide. Here the left hand side, the number of elements of group G, order of G is divided by P, and also right hand side the second term, summation A does not belong to Z of G, order of G divided by order of n of A also divided by prime number P. So therefore automatically the order of Z of G is also divided by P, that is P divides order of Z of G. Here Z of G is a subgroup of G. Now we know that P divides an element order of H, so therefore here the center of group G will be equivalent to G. Therefore G is abelian. The result is true for abelian group. So therefore there exists an element A belong to G such that A power P equal to E. Next we give the example for the Cauchy's theorem. So consider the set S3. S3 is nothing but the set of all permutations of the form identity E 1 2 1 3 2 3 1 2 3 and 1 3 2 are the totally 6 permutations will have. Identity permutation E, it maps into itself 1 mapped to 1 1 1 2 2 3 3. Now we find the value of 1 to the whole square, that is the 1 2 is nothing but 1 mapped to 2, 2 mapped to 1 and 3 remains as it is. And here it repeated 2 times, and then in the first row for first matrix 1 mapped to 2, and in the second matrix we see that 2 mapped to 1. So therefore finally 1 mapped to 1. Similarly you see the left side in the left hand side matrix 2 mapped to 1, and then in the come to right side 1 mapped to 2. So therefore finally 2 mapped to 2. Here consider the elements in the left hand side alone first. Here in the first matrix the 3 in the row, first row mapped to 3 in the second row, 3 mapped to 3, 3 mapped to 3. So therefore finally you will get the identity permutation E. Similarly 1 3 whole square also can be mapped as, in the first matrix we see that 1 mapped to 3, in the second matrix we see that 3 mapped to 1. So therefore finally we will get 1 mapped to 1. So from the left to right you have to make calculations. So here in the first matrix 2 is mapped to 2, and in the second matrix also you go that 2 mapped to 2, finally 2 mapped to 2. In the left matrix 3 mapped to 1 and 1 mapped to 3. So finally it mapped to 3 is the answer. So now the 1 2 while we are getting when the permutation 1 2 is repeated twice times, you will get an identity permutation E. So therefore the order of the permutation 1 2 is 2. Similarly order of the permutation 1 3 is also 2. Order of permutation 2 3 is also 2. Similarly we can find out. And next we see that 1 2 3 the whole cube, when 1 2 3 is the permutation 1 2 3 is multiplied 3 times, we will get the identity permutation. So therefore order of the permutation 1 2 3 is 3. The order of the permutation, similarly we can find the order of the permutation 1 3 2 is also E. Now thus we have seen that we know that the S3 consists of 6 permutations, therefore order of S3 is equal to 6. That 6 can be written as 2 into 3. Now the element 2 divides the number of elements of the group S3, that is 2 divides 6 as well as 3 divides 6. Now from the result we have seen that there are 3 permutations, namely 1 2, 1 3 and 2 3, whose order is 2. And we are having 2 permutations 1 2 3 and 1 3 2, whose order is 3. So therefore S3 has 2 elements of order 3 elements of order 2. Now next we see the definition. For any integer n, we say the sequence of positive integers n1, n2, n3, etc. nr which are formed such that n1 less than or equal to n2 less than or equal to n3, etc. less than or equal to nr. This sequence of positive integers will constitute a partition of n, that we are going, that if n equal to the sum of the values n1 plus n2 plus n3 plus etc. nr, and let P of n denote the number of the permutations of n. Now here we can see that 1 can be written as 1. Suppose you take as 1, then there will be equivalent value, it will be written as only one time. So therefore the number of partitions of 1 is 1. But at the same time, the element on the 2 can be, the number 2 can be written in two forms without violating the condition, that is n1 less than or equal to n2 less than or equal to n3. So the element 2 can be written as 1 plus 1. The first element 1, the second element is also 1. Now here the condition is the higher now here therefore the 2 can be written as 2 itself. So therefore P of 2 is equal to the number of the 2 can be written in partition in two ways, 1 plus 1 comma 2. So therefore P of 2 equal to 2. Similarly the 3 can be partitioned as 1 plus 1 comma and then 2 plus 1 1 plus 2. We reverse order we can write it as because the value of n1 must be less than or equal to 1 2. So if you take n1 as 1 and n2 as 2, that is you write it as 1 plus 2. So there are three possible chances for the number 3 can be partitioned in a ways. The ways are 1 plus 1 comma 1 plus 2 comma 3. So therefore the number of partitions of the permutation here is 3. Similarly the 4 can be written in the form 1 plus 1 plus 1 plus 1 then 1 plus 1 plus 2 then 2 plus 2 and 1 plus 3 without violating the condition n1 less than or equal to n2 less than or equal to n3. And finally the 4 can be written as a single value 4. So therefore the number of partitions of the number 4 is P of 4 equal to 5. Similarly we can find the partition number of partitions for the number 5. The 5 can be written as 1 plus 1 plus 1 plus 1 5 times and then 1 plus 1 plus 2. While we are adding the numbers, you will get the final number. That is the condition. That is final n must be equivalent to n1 plus n2 plus n3 plus nr. That condition must be the two conditions must be verified. Based on that we are forming the partitions. The one condition is n1 less than or equal to n2 less than or equal to n3 etc. nr, and the second condition will be equivalent to the sum of the partitions will be equivalent to n. So from this we can see an result. Each permutation in Sn is a product of the disjoint cycles. If cycles have the length n1, n2, n3, nr respectively, such that n1 less than or equal to n2 less than or equal to nr, then n can be written as the sum of the cycles of length n1 plus n2 plus n3 plus etc. nr. That is each permutation in Sn gives a partition of n. Let us prove this result by an example, by giving an example. We take an S9 permutation. So S9 consists of 9 elements. Here 1 mapped to 1, 2 mapped to 3 and 3 mapped to 2. So therefore there a cycle is formed between 2 and 3. So therefore you write is 1 mapped to 1 itself a single, a cycle of length 1. A cycle of length 1 is written within the brackets 1. And similarly the 7 itself 7 mapped to 7 itself. So therefore there is a cycle, one cycle for 7 we write one cycle again, and here the 2 mapped to 3 and 3 mapped to 2. So one cycle is formed with the help of the elements 2 and 3. So therefore 2 and 3 can be written as one permutation. Similarly so now 4 mapped to 5, 5 mapped to 6 and 6 mapped to 4. So therefore 4, 5, 6 form another permutation. Similarly 8 mapped to 9 and 9 mapped to 8. So therefore 8, 9 form one permutation. Now you count the number of elements in the each permutation. The first permutation 1, in the second permutation you will have 1 element. In the third permutation 2, 3 you are having 2 elements, and third permutation, fourth permutation 3 elements, and fifth permutation 8, 9 you will get another 2 elements. So therefore while you are adding the number of elements in the partition permutations, you will get the Sn, the number of order of the elements, number of elements in the set Sn. Next, suppose the order on the theta and sigma belong to Sn. Now consider the mapping theta inverse sigma theta. Find this mapping. So you have to find the value for theta inverse into sigma theta. Now let assume that theta is a permutation formed by 7 elements. So one permutation is 1, 2, 3 and another permutation is 4, 7, which are expressed in terms of product. Similarly, sigma is also written as the product of the two permutations 5, 6, 7 and 3, 4, 2. So therefore 3 can be written as 1 mapped to, you write the all the elements 1, 2, 3 up to 4, 7 in the domain element. The numbers in the the numbers in the first row are called the domain elements, and the numbers in the second elements are called the codomain elements, which are images of the domain element. So therefore the image of 1 is 2, the image of 2 is 3, and the image of 3 is 1. One cycle is formed. And another one, the image of 4 is 7 and the image of 7 is 4. And the between the elements of the 5 mapped to 5 and 6 mapped to 6. So we have framed the theta. Similarly, we can find the value of sigma also. Then after that we can find the inverse of the permutation theta. That means in the second row, see where it comes 1, the corresponding to 1, the domain element will be the inverse element. Here in the against the theta, the inverse image of 1 is 3. So therefore we have written as 3. And here the from the permutation theta, the inverse image of 2 is 1, namely the domain element. நீங்கள் upper side பார்க்கணும். அது மாதிரி similarly the inverse image of 3 is 2. So therefore you write 2 here. And the inverse image of 4 is 7. So therefore against 7 we have written 4. We are finding the inverse images. That is we are finding the image for the elements in the second row to the first row. So அதுதான் நம்ம பார்க்குறீங்க. And here the 7, the inverse of 7 is 4. The inverse of 5 is 5. The inverse of 6 is 6. So we have found the theta inverse. And next we find the sigma of theta. Sigma theta already we have discussed. From the left hand side matrix to you have to go to the. So therefore find the image of the element for sigma. Write the sigma permutation and theta permutation. So first you permute, find the image for it. So from the left side in a matrix 1 mapped to 1, and see the right side matrix here there 1 mapped to 2. So therefore final answer 1 mapped to 2. Similarly in the left matrix you see that the element 2 mapped to 3, whereas in the right side matrix 3 mapped to 1. So therefore finally 2 mapped to 1. I mean similarly we can find the in the third element of the first row 3 mapped to 4, whereas in the second matrix 4 will be mapped to 7. So therefore finally 3 mapped to 7. Similarly we can frame the on repeating procedures we can find the value of sigma theta, and after finding the sigma of theta value you permutate with the theta inverse. So again applying the same rule you will get the answer will be 1 mapped to 7, 7 mapped to 3 and 3 mapped to 1. So therefore 1, 7, 3 form a cycle. 2 mapped to itself. So it is a cycle of length 1. And we see that 4 mapped to 5, 5 mapped to 6 and 6 mapped to 4. So therefore 4, 5, 6 form a then a cycle. One permutation, sorry. So thus the two permutations have the same cycle decomposition. So therefore they are conjugate. Next we prove the theorem. The number of the conjugate classes in Sn is P of n. That is the idea that we are going to prove it now. That is two permutations TW. Two permutations in Sn are conjugate if and only if they have the cycle decomposition, that we have to prove it now. So first take two permutations. One permutation sigma s, it is expressed as the product of the nr permutations. The first permutation consisting of the elements a1, a2, a3, etc. an1, and the second permutation will have elements b1, p2, p3, etc. bnr, bn2, and therefore the nth permutation will consist of x1, x2, x3, etc. xnr. And similarly the permutation tau can be taken as one product of the permutations alpha 1, alpha 2, 3, alpha n, one permutation, beta 1, beta 2, beta 2, beta 3, beta n2 is another permutation, etc. Now sigma and tau have the same cycle decomposition. Now by theta is obtained by permuting the above permutations sigma and tau. The sigma is we write the sigma matrix. The sigma matrix is A1, A2, A3, AN1. Here to the corresponding values, the sigma elements of A1 will be mapped to the alpha 1 element of tau. So A1 will be mapped to alpha 1, A2 will be mapped to alpha 2, etc. A3 will be alpha 3 and AN1 will be mapped to alpha n1. Similarly, B1 will be mapped to beta 1 n, B2 will be mapped to beta 2, etc. Beta n2 will be mapped to beta n2. So this is the matrix, this is the permutation theta obtained by composition method. So therefore now we find the value of theta inverse sigma theta. Now theta inverse is nothing but the reverse elements. Theta inverse is alpha 1, alpha 2, etc. alpha n into sigma is beta 1, beta 3, beta n2, and here so therefore theta inverse sigma theta can be expressed as the permutation tau. So here the permutation theta equal to Sn symmetry group and tau equal to theta inverse sigma theta. So therefore sigma and tau belong to the same conjugate class. By the definition of conjugate class definition, we see that there exists a theta in Sn such that the tau equal to theta inverse sigma theta. This is the definition of conjugate class. Now conversely assume that the sigma and tau belong to the same conjugate class. So then what will happen? And that is there exists an element of the theta belong to Sn such that t equal to theta inverse sigma theta will be hold. Now this sigma inverse theta inverse sigma theta theta inverse sigma theta is got by replacing the elements of sigma by its image under theta. So therefore sigma inverse sigma and theta have the same cycle decomposition. So thus we have proved that sigma and tau have the same conjugate class if and only if they have the same cycle decomposition. So therefore finally we see that a cycle of the decomposition gives you a partition of n. Therefore the number of elements in each conjugate class is the number of the permutations P of n. So thank you students.